Okay, in today's lecture, we're going to look at the inverse class F amplifier, which is kind of the opposite of the class F amplifier. Remember, in the class F amplifier, we squared the voltage waveform and half rectified the current waveform. In the inverse class F, we're going to square the current waveform and half rectify the voltage waveform. So here we have our drain current waveform. And our drain voltage waveform. Ideally, they're non-overlapping, and they repeat periodically every 2 pi cycles. We can do a similar Fourier analysis on the inverse class F that we did on the class F amplifier. Here, I'm just going to provide the fundamental voltage and current coefficients. We can find the output power as the product of the RMS voltage and RMS current at the fundamental. Similarly, we can find the impedance at the fundamental and the impedances that we need at the harmonic frequencies. So we can find that the impedance required at the fundamental is equal to pi squared over 8 times VDD over ID. This is our optimum termination impedance. If we substitute the output power that we found in the previous equation, we can find the optimum termination impedance in terms of the supply voltage and the desired output power. Now we note that in the case of the inverse class F, we want to square the current waveform and rectify the voltage waveform. And this means that at odd harmonics, we want a short circuit, and at even harmonics, we want an open circuit. This means at Z of 2n plus 1, we want a short or zero impedance, and Z of 2n, we want to be infinite or open circuit. Now we can design a simple example inverse class F, but most of the principles that we used for the class F in the prior lecture apply here. Here we've placed a parallel resonant circuit in series from the drain of the transistor towards the output resistance, and this is resonant at the second harmonic. And we have a shunt parallel resonant network in parallel with the optimum termination resistance, and this is resonant at the fundamental. Okay, so let's examine how this works. At high frequencies, C1 and C2 are low impedance. This means that they're low impedance at high even harmonics. Here, the second harmonic sees the high impedance of L2 in parallel with C2. In other words, that parallel resonant tank that's parallel resonant at F2. All of our odd harmonics see the low impedance of C2 in series with C1 at those higher frequencies. So the analysis that we did for our gamma V and gamma I the other day, the opposite of that analysis applies here. In this case, we've only terminated one even harmonic, so we have a suboptimal class F. I should say we have a suboptimal class F inverse. And generally, we would expect if we were to terminate more harmonics that would result in the voltage waveform being more half rectified. In other words, more even harmonics, we would get a better improvement in the efficiency. So we're going to stop there for the day. Now we've seen the class E amplifier and the class F amplifier, and the next lecture we're going to look at the class D amplifier. But one of the things that we should note at this point is that there's a clear distinction between our linear amplifiers, class A, AB, B, and C, and our switching amplifiers, class D, E, and F. And the primary difference is that we improve our efficiency in linear amplifiers by modifying the bias point, whereas in switching amplifiers, we improve the efficiency by modifying the pulse shaping networks at the drain of the transistor.